If you've been paying any attention at all to technology news, and I mean really any of it, we're living through a tectonic shift. The speed at which AI is being developed, adopted, and deployed is just, it's absolute staggering.
It is. And that velocity is creating this immense value, but it's also creating complexity at a rate we've just never seen before.
Right.
And when systems change that fast, you're basically introducing chaos. And chaos, in a production environment, that translates directly into outages, security holes, and ultimately millions in lost revenue.
But there's a way to manage that chaos.
There is. There's one disciplined practice, one really foundational principle that pretty much determines whether this whole AI rollout succeeds or if it just fails.
And that's configuration management.
That's it, configuration management.
Which I have to say, it sounds like maybe the least glamorous topic in the world. It often gets lumped in with, boring systems engineering bureaucracy.
It does. But you're making the case that it's actually the essential, non-negotiable bedrock for every single scalable AI system we build from now on.
That's what the sources are pointing to.
Exactly. And that's our mission in this deep dive. We're going to use your sources as a roadmap to understand precisely why CM is required to manage this massive, unique complexity of modern AI pipelines.
It's the difference between a system that runs reliably and one that you just can't reproduce.
You can't reproduce it and you can't trust it.
Okay, so let's unpack this. When we talk about configuration management, we aren't just talking about some checklist, right? What exactly is the working definition here?
At its core, CM is really a disciplined practice. It's about establishing and then maintaining the consistency of a system's functional and physical attributes.
Throughout its entire life cycle.
Throughout its entire life cycle. And you should really think of consistency as control.
Yeah.
If you lose control over what state your system is in at any given moment, you can't trust its output, period.
So consistency is the goal. But for a huge multi-environment system, like an AI service that's running across a cloud cluster and also on some edge device somewhere, how does CM even begin to achieve that? It must be tracking just an overwhelming amount of detail.
Oh, it's exhaustive by design.
Yeah.
It has to be. CM identifies and tracks every single component that makes up that environment.
And you mean everything?
Everything. So we're talking about the obvious things first, like the application source code and the specific versions of, your programming library.
Sure.
But then we also track the compiled binaries, the deployment configuration files, the data schemas, even the specific hardware settings down to the CPU configuration on the server.
And the network topology.
And the network topologies. And crucially, for today's world, this also includes the definitions for the cloud services themselves.
That feels like the key expansion point, doesn't it? The physical environment used to be a rack of servers in a closet.
Exactly.
Now the physical attributes are literally defined in code.
Absolutely. And that's where infrastructure as code, or IAC, comes into play. These IAC platforms basically let you treat the creation and configuration of your entire server, network, and cloud setup, the physical attributes, as just another piece of versioned code.
So the deployment environment itself becomes this auditable component inside the CM system.
Precisely.
And if you miss one variable, one obscure library version, one cloud service setting that's different between staging and production, the whole thing breaks and you have no idea why.
That's the nightmare scenario.
So that must be the whole rationale behind creating what the sources call the single source of truth.
It is the ultimate goal. Every single item we've identified, its specific version, its relationships, all of its dependencies, gets cataloged in a controlled repository. That inventory is your definitive configuration.
So when you want to make a change, you don't just log into a server and edit some file.
No, you change the definitive configuration list, the source of truth.
And that's where the discipline gets enforced. So this isn't passive filing. This is active enforcement through tools.
Right, through your version control systems, your automated build pipelines, and those IAC platforms we mentioned.
And what's the consequence of a change flowing through that kind of discipline process?
The consequence is absolute traceability and automated validation. The system mandates and captures who made the change, when they made it, why it was requested, and this is key, what impact it has on every related component.
And before it even gets deployed.
Before it ever gets deployed, the CM system validates that the new state is actually compatible with the existing architecture.
I remember the old days, the classic developer headache of, well, it works fine on my machine. Why is the staging server broken?
Mm-hmm.
CM seems like the definitive answer to that decade-old problem.
It is the definitive answer, and the payoff is monumental. The primary goal is ensuring that a system can be reliably reproduced, audited, and rolled back to a known good state at any point.
So if you have an outage at 3 a.m.,
You don't troubleshoot. You use the CM system, you find the last known stable baseline configuration, and you roll back to it. You minimize the downtime. That capability is powered entirely by CM. That makes perfect sense for traditional software, where the code is really the primary moving part. But let's bring in the chaos factor. AI.
AI development is incredibly fast. It's often non-deterministic. It's constantly shifting with new data.
Yeah.
Isn't this kind of rigid, disciplined CM going to slow down the very velocity that AI needs to be successful?
That is the critical question, and it really flips the script. The discipline doesn't slow down the velocity, it enables it securely.
How so?
Well, the core conflict is that AI pipelines are intrinsically far more complex than traditional software pipelines. They deal with 4 different types of versioned assets that have to stay in perfect sync.
Okay, so walk us through those 4 assets. Why do they break the old models?
So you have the code, which is traditional. You have the infrastructure, which we covered with ISE. But the complexity just explodes with the other 2, the data and the models. The data itself is a configuration item. In AI, absolutely. The training data, the data schema, that is configuration. If you update your model code, but you accidentally use a configuration for a different, older data set, the model will fail or it'll suffer from what we call model decay.
Model decay. That sounds like a silent killer for a project.
Right.
Can you give us a real-world example of how that happens?
Sure. Imagine a system that classifies loans. Your model, version 3.5, was trained to expect 50 input features, including one called FICO Score Bracket A.
Okay.
Then, a data engineer working completely separately updates the internal feature store and renames that field to FICO Score Bracket B. They think it's a minor change.
But without CM tracking that data schema version and linking it directly to that model version.
The model is now getting incompatible inputs. It doesn't crash, but its output quality just plummets because the fundamental configuration, the data structure, has drifted without the model's knowledge.
So the configuration isn't just a bunch of static files. It's a dynamic relationship between the logic, the specific version of the data, and the hardware it all sits on.
Exactly. And that complexity is just amplified by the sheer speed of development you mentioned earlier.
Right.
Think about the rapid iteration cycles in modern MLOps. We're not talking about weekly code pushes. We're talking about continuous model training, A/B testing, and these advanced concepts like hyperparameter sweeps and automated machine learning.
Let's pause on hyperparameter sweeps for a second. Explain why that generates so much complexity.
Okay, so hyperparameters are the high-level settings that govern how the model actually learns. Things like the learning rate, the batch size, the optimization algorithm.
Got it.
So when a researcher wants to find the best performing model, they run these automated sweeps, hundreds, maybe thousands of simultaneous experiments, each with a different combination of those parameters.
And every successful one of those experiments creates a unique versioned model.
A unique versioned model artifact, linked to a specific configuration of training data and hyperparameters.
So if you're generating thousands of versioned artifacts per day, and you lose the precise record of which combination produced the model you have in production,
You have instantaneous, unmanageable drift. And that's where CM, maybe extended with tools like beta version control, steps in to provide that critical, anchored, single source of truth.
it's the necessary anchor.
It is. Without that centralized, auditable record, you cannot replicate a successful outcome, you can't debug the model's behavior, and you certainly can't assure anyone, internally or externally, that it is operating as intended.
Okay, let's transition now from sort of internal team stability to the external pressures, the world of regulation and risk. Because once AI moves out into the wild, CM suddenly becomes this critical compliance shield. It moves beyond just being technically useful and into being legally necessary.
This is a huge accelerant for CM adoption. The world is reacting to AI with some very serious mandates. Your sources specifically call out the EU AI Act, the US AI Bill of Rights, and global standards like ISO 42001.
Which is the international standard for AI management systems.
Right. And these regulations, they demand unprecedented levels of accountability.
And what's the specific thing they're demanding that CM is just uniquely positioned to provide?
They demand auditable provenance. That means a complete, unassailable paper trail tracing the lineage of every single deployed model.
So regulators need to know everything. Was this model trained on compliant data? What exact version of the configuration generated this specific outcome?
And critically, why were these hyperparameters chosen over others? You have to be able to answer that.
So in a highly regulated field like finance or healthcare, saying We think we use version 4. Just isn't going to cut it.
Not even close. CM, with its strict traceability, provides that instant hash-level proof of lineage. You can prove that the model you deploy today is the exact same one you tested yesterday, and that it was built according to the specific rules in your compliance framework.
That's impossible without CM governing the whole stack. And that same traceability becomes vital when we talk about security, right? Because modern AI workloads rely on this incredibly complex and, frankly, vulnerable supply chain.
The risk landscape for AI is just fundamentally different. It's a dependency minefield. You're relying heavily on specialized open-source frameworks like PyTorch or TensorFlow.
You might be using third-party data sets.
Right, third-party data sets, specialized hardware accelerators, often from different vendors. Your attack surface is massive and it's fragmented.
So if a big vulnerability is discovered, let's say the AI equivalent of that Log4j catastrophe, some flaw in a core ML library, you can't just assume you're safe.
No, and CM is essential here because it maintains that definitive inventory of all your components and their versions. When that vulnerability is announced, CM is the tool that lets you instantly query your entire deployment landscape.
Across development, testing, and production.
Across everything. And you can identify exactly which models and services are relying on the compromised version of that library. It enables targeted, rapid patching instead of a frantic manual search across thousands of configs.
So CM helps you track the inputs, but it's also necessary for keeping the resulting AI service running reliably across these wildly different operational settings. Which brings us to operational resilience.
Right. The operational challenge is all about configuration parity. AI services aren't monolithic. They often run in these hybrid environments. You might train in a massive cloud environment, deploy for inference on a smaller one, and then push optimized versions out to hundreds of edge devices.
In factories or retail stores or wherever.
Exactly. And if those environments aren't configured identically, failure is pretty much guaranteed.
It is.
So CM is the underpinning technology that guarantees that the specific configuration you validated in the cloud is identically mirrored wherever that service is deployed.
On-premise cluster, low-power edge device, it doesn't matter.
It doesn't matter. If a component fails on one of those devices, CM ensures you have that reliable rollback capability. If you can't reproduce a working environment consistently, you can't recover from a failure reliably. That is the definition of operational resilience in the age of distributed AI.
This whole conversation paints a picture of CM being so much more than just systems bureaucracy.
Yeah.
It's the governance layer you need to manage systems that are defined by this exponential complexity and velocity.
That's the exact synthesis we need to draw. If an organization looks at implementing robust CM and thinks, oh, that's too much overhead, they are completely missing the point. The cost of neglecting CM is so much steeper, and it's compounded by the nature of AI.
What is the practical impact of that neglect? What are you seeing in the field right now?
It's severe. Organizations are risking serious non-compliance penalties given the global regulations we've talked about. They're highly vulnerable to security breaches because of untraceable dependencies.
They're facing constant, costly outages.
Constant outages because they don't have reliable rollbacks. And fundamentally, they risk financial loss through model decay, where the value of their core asset, the AI model, just silently degrades because of unmanaged configuration drift.
And here's the crucial final detail, right? These risks, all of them, are amplified by the velocity and the opacity of AI systems. Because AI changes constantly and its internal workings can be, a black box, you need that external layer of governance, that audit trail, to impose some sanity.
You do.
So configuration management is really the necessary foundation for turning this chaotic, ever-changing collection of data, code, and models into a system that is manageable, predictable, and auditable.
It's the only way to ensure that the promise of rapid scaled AI deployment actually becomes a reality and not just a source of constant system failure. CM provides the predictable, auditable ground that AI needs to be trusted and scaled responsibly.
That's a really comprehensive look at why this dry practice is actually the single most critical factor in the next decade of technology.
Absolutely. And given that CM's entire purpose is to ensure a system can be reliably reproduced, audited, and rolled back.
And that it enables the traceability required by regulators.
Right. It leaves us with a provocative thought for you to consider. If CM provides the definitive paper trail of who configured what and why leading up to a specific outcome, what does that transparency ultimately imply about who bears the legal and ethical responsibility when an autonomous AI system causes significant harm or fails in the future?
The technology is consistent.
The technology is consistent, but the accountability is now traceable. And that moves the discussion entirely beyond just technical consistency and squarely into the realm of institutional responsibility. Until next time, keep exploring, keep questioning, and keep diving deep.
Thank you for listening to today's podcast. Please feel free to click on the link in the description below to discover more podcasts.